All right. So if you look at the code we have written, which are the components that we can reuse? Well, first let's look at the approximation for the derivative. That can be reused with no problem, right? So it's basically finite difference. We can do finite difference to one variable. We can do it with two variables. The extrapolation has no problem also. And the limiter also shouldn't have any problem, right? So we can use the same limiter to limit the extrapolation. Now, the only problem comes in the Goodenough scheme. And in general, the task of finding how a discontinuity would evolve in a system of conservation laws is highly non-trivial. I mean, there is actually no general analytical solution for how a discontinuity would evolve. So, for example, if you have the equation for fluid flow, the gas dynamics equation, a typical discontinuity would actually evolve into three separate things. You have a shock wave that travels in one direction. You have a so-called a contact discontinuity that involves a temperature change, discontinuous temperature, and discontinuous density that travels in another direction. And you also have a rarefication wave. Basically, you also have a wave that is no longer basically something that starts as a discontinuity and slowly becomes another discontinuity that travels yet in another direction. So the analytical solution is remarkably difficult to find. And the more equations you have, the harder it is to find the analytical solution for the so-called Riemann problem, which is solving for how a discontinuity evolves. So for system of equations, the most general solution is to approximate the solution of a Riemann solver, or of a Riemann problem, is to not actually find an exact solution. But how do we guarantee that we can still have a good solution? And particularly, remember, like the reason we introduced the Goodenough scheme is because there can be not entropy satisfying solutions if we're just using upwinding, right? So we can choose the basically Goodenough scheme not only chooses which side of the flux we want to use, it also introduces the case where it doesn't choose either, right? If the remember for the f equal to u squared over 2 case, and if my if my WL is over here, WR is over here, the flux is actually chosen to be 0. So how do we deal with this kind of cases if we have a system of conservation laws? The idea really comes from the fact that upwinding really introduces numerical dissipation, right? As we analyzed in the finite difference case. If we choose to upwind in the upwinding direction, we are actually introducing numerical dissipation. And you can show that if we introduce enough numerical dissipation, it really prevents the non-physical solution to appear. So a non-physical solution, as we have seen in finite volume lectures before, is that if I have a discontinuity where on the left-hand side is negative, on the right-hand side is positive, this discontinuity may actually, if you don't use a Goodenough scheme, but rather just try to upwinding in one way or another, we can have this non-physical solution to be maintained in our numerical solution. But this wouldn't be the case if we introduce enough numerical dissipation. The numerical dissipation, if we introduce, for example, a delta x over 2 times a second order derivative of w on the right hand side, okay? So this is like the numerical dissipation we have in finite difference. It would immediately smooth out this discontinuity into something not discontinuous anymore. And it'll prevent this non-physical solution to be stationary, right? So this it'll basically smooth out the solution, and the smooth out solution is going to evolve actually physically. So another way to solve the problem of entropy violating solution is to introduce numerical dissipation. And a good approximate Riemann solver actually would introduce the minimum amount of numerical dissipation to make a entropy satisfying solution. Okay, so the goal of approximate Riemann solver is basically to introduce numerical dissipation to smooth out non-physical discontinuities. All right. Okay. So now the question is, how much dissipation should we introduce?